This talk is about the PLATO mission. I will tell you about its science objectives, its instrument, and its current status, and I will do so on behalf of the whole PLATO team. PLATO is the M3 mission in ESA's Cosmic Vision program, and the diagram shows you how it fits into the context of past, ongoing, and future extrasolar planet missions. PLATO is launched for the end of 2026, and in the ESA program, it will follow the very successful ongoing Cheops mission. So why do we want another mission about transit detection of planets for a timeline after Kourou, Kepler, TESS, Cheops? Well, one reason to look at it is shown here. We see the mass versus semi-major axis of known extrasolar planets, and we see the parameter space of the solar system is still largely unexplored. In particular, for the small planets, we want to characterize them around stars that are similar to our sun. We need another mission, and PLATO will aim at exactly this parameter range, as I will show you now. PLATO will determine the radius and mass of planets and therefore its mean density. Why do we want to do that? Well, for characterization, the mean density, in particular of small planets, is interesting and gives some indication about the nature of the planets. And this is shown here to the right. We see the density versus radius of the terrestrial planets in the solar system, and we see they are nicely lined up. But there's one oddball here, and that is Mercury. If somebody would come and take mean densities and radii of planets in our solar system, you would immediately see something has been different. Something is different with Mercury's formation or evolution history. When we see the mean density versus mass of extrasolar planets, we can see two regimes: the low mass planets, the giant planets, and here to the right, we see the relationship of stars, of density versus mass for stars. We see for the giant planets, there is also a very clear correlation of their mean density with their mass. But for the low mass planets, this is different. We see a very large scatter ranging from terrestrial planets like our Earth up to Uranus, Neptune type planets, and many things in between. There's a huge diversity. And whether this diversity corresponds to different types of planets, if we can see populations here in this regime, all of this is at this point unclear because error bars in mean densities and masses are still relatively large. Another way of looking at it is here in the radius mass diagram that you are maybe more familiar with. We see the known extrasolar planets and the error bars here, and we also see the dashed lines which correspond to planets of different compositions, from iron to pure water planets. The currently known extrasolar planets in this diagram, in particular the small ones, cross many of these dashed lines. The error bars are large and we cannot exactly pin down where they fall here and what is their composition. The goal for PLATO is to refine these error bars, and for an Earth-sized planet around a solar-like star, which I must say is our benchmark case and also the most difficult case, here we aim at a precision of 3% for the radius of the planets and 10% for their mass, and the red rectangle here shows approximately what that means in this type of diagram. We must be aware, of course, that I'm simplifying the story here a little bit. Of course, there are degeneracies. In particular, for these small planet regimes, we already know there are planets which are similar to the Earth. That means mainly rocky planets with only a thin envelope of an atmosphere. But there are also planets which have a dense core, rocky core, and a huge hydrogen envelope. So for the same radius and mass, we can find very different compositions. So PLATO's radius and mass measurements will provide precise constraints, and that will help, but they cannot resolve these degeneracies alone. At the end, we need to combine all information that we can get about extrasolar planets to disentangle them and to understand the huge diversity. So fortunately, planets detected by PLATO will orbit stars that are bright And so they will allow for transit follow-up spectroscopy, for example, to investigate their atmospheres. At the end, all missions together will help us to disentangle the big puzzle to understand planetary nature. This diagram is taken from a reanalysis of Kepler data that has been performed recently. And we know from Kepler that basically every star in the sky has a planet. We also know that about 17% of the dwarf stars may have a super Earth. But the occurrence rates of small planets in the habitable zone are not very well known yet. And this is defining the main search range for PLATO. Another way to show that is here in this diagram, which shows the stellar mass versus the semi-major axis of planets. We see the solar system with Mercury, Venus, and Earth, and the green belt shows the habitable zone. And the habitable zone moves closer to the star as we move to smaller stellar masses. So here we have the M dwarf regime, and here we already see the planets that are characterized for their radius and mass in the habitable zone of these stars. And we expect many more of them to come from TESS in particular. So TESS will fill this diagram here in the next years to come. But what is left open? What is left open are still the large orbital distances of solar-like stars where you need long, uninterrupted observations of many of these types. And this is the search range for PLATO. So PLATO will search for planets in the habitable zone of solar-like stars. That's where we want to put our focus. It will determine whether they are rocky planets, and it will determine the age. And all of this will help us to understand better how planets form and how they evolve, and how our system compares to other similar planets in our galaxy. And again, we provide targets for future atmosphere studies as well. So combining the methods of PLATO, PLATO will provide light curves, precise light curves that are used to search for transit events to detect extrasolar planets and determine the planet to star radius from them, from the transit shape. The light curves will also provide the information for astroseismology of the host stars. And astroseismology analysis will be used to get the stellar radius, stellar mass, and age of the system. And in combination with high precision radial velocity information from the ground, we get the true planetary mass and the eccentricity of the system. So all of this together allows us to derive the planet parameters to the precisions mentioned here, 3% for the radius, 10% for the mass, 10% for the age, for a bright Earth-Sun analog. And why do we want to do that? Well, this is indicated in this illustration to the right, because we know planets change with time. We know from the solar system, the terrestrial planets in particular had a very interesting history. They starting with a magma ocean phase, and then maybe in case of Earth, we had plate tectonics. Venus and Mars did not have plate tectonics. We have secondary atmospheres, outgassing, and in case of life for the Earth, even a change to a tertiary atmosphere. And all of this is happening in parallel to a star that is also evolving. So getting precise planet parameters together with precise ages of planetary systems will allow us to look at planets in a very different way than what we are used to when we had only the solar system. We have to combine all of this information together to understand planet evolution in a similar way as we once understood stellar evolution. So talking about stars, I mentioned already, PLATO will not only search for planets, it will also investigate the stars by astroseismology. This is very important, otherwise we could not achieve the planet parameters. We need very precise stellar parameters. But there is more to say to this. And this diagram, this HR diagram shows where pulsations of stars are found in the dataset. And the core program of PLATO focuses on solar-like stars, for which we want to determine 2% in radius, 10% for age. And we will get that for about 1,000 of these stars that are then used to calibrate more classical age determination methods. But this is only addressing a very small range in the HR diagram. There's much more to do with data like PLATO. And for this, we have 8% of our data range that is reserved for the guest observer program. And the guest observer program can address anything you can think of to do with PLATO data. For example, looking for flares, for binarity, for rotation, for distance scales, galactic archaeology, transient events. So think about what you can do with PLATO data and apply for the guest observer program. A call will be issued by ESA 9 months prior to launch. So now let me come to the PLATO mission itself. As I said, PLATO is the third M-class mission of ESA. It is currently in phase A, and the critical design review has just started. It's launched for end 2026. It will go into an orbit around the L2 Lagrangian point, allowing it to access a large fraction of the sky. It will provide precise photometry for stars in the range from 4th to 13th magnitude. And for the bright stars, brighter than magnitude 11, it will provide a precision of 50 ppm in 1 hour. The approach of PLATO is somewhat different to what you are used to from a classical telescope. Instead of having one single dish telescope, the aperture is divided into 26 individual cameras. And we see here the spacecraft from the side with the 26 cameras. Here it is coming around. Sorry. And here in the bottom, we see the mass and thermal dummies of 4 of these cameras to give you a feeling how this looks like in the real world. We have 24 cameras, which we call normal cameras. They have an aperture of 12 centimeters each. And these cameras are separated into 4 groups, which are mounted on an optical bench. They are fixed mounted in 4 groups, and these groups point at the same region of the sky, but not perfectly. They are opened by an angle of 9 degrees to increase the field of view somewhat to cover a larger region of the sky for transit detection. What that means is shown in this flower-like diagram here on the right, where the field of view of these 4 groups is shown as it overlaps. So in the center of the field of view, we have 24 cameras looking at the same region of the sky. And in the corners of this field, we have the 6 cameras of one section looking at the same field in the sky. Now, each one of these cameras has 4 CCDs with a pixel scale of 15 arcseconds per pixel. They operate in white light, and these normal cameras provide a data point every 25 seconds. The fast cameras, shown here on the top, they are called fast because they have a higher readout cadence of 2.5 seconds. And their task is twofold. First, they cover the bright end of our photometric range. And they do that with a red and a blue camera. So we have a coating on each one of them, red and blue. But they also serve as key elements in the fine guidance of the satellite to support the accurate long-term pointing stability of the mission. Now here we see to the left an illustration how the fields of PLATO would look like on the sky. And you see 2 dark blue fields, one in the north and one in the south. This is in galactic coordinates. The green ones are K2, red is Corot, and the Kepler field here in yellow, to have a comparison in the size. So you see how big the PLATO field is and which fraction of the sky it can cover. With the current baseline of the mission, we have a phase of 4 years operation. This is the standard operation phase for a new mission of ESA. And as a baseline, we have divided these 4 years in 2 long pointings. So 2 years in the south, 2 years in the north. Of course, there's an alternative to just keep one pointing and stare at it for 4 years. or also other combinations, for example, with smaller short pointings, which can be located at different places in the sky, is possible. The final observing strategy will need to be fixed 2 years before launch, but it can also be adapted during the mission, so we are quite flexible. I should also say that the mission has consumables for 8 years, so in principle, we can ask either for mission extensions up to 8 years. To recall and to remind you the comparison to TESS, here we have the TESS observing strategy covering the whole sky in the northern and southern hemispheres, which are almost covered twice now. And of course, there will also be mission extensions possible. So TESS has a relatively small continuous viewing zone, small in comparison to PLATO. You can see the two missions have been maximized for different purposes. TESS wants to discover the planets, the bright, short period planets over the whole sky, whereas PLATO is really targeting at long periods, and that means we have to keep staring at the field of the sky for as long as possible with uninterrupted observing sequences. So very different observing strategies of the two missions, which are very complementary, I should say. PLATO, with 26 cameras covering such a big fraction of the sky, it's impossible to download full frame images at the data rate that we are taking data. So we can download only imagettes, or you call them postage stamps. That means we need an input catalog for the mission. At this point today, what we have is an all-sky catalog of potential targets for PLATO, which has just been published in PLATO et al. 2021. And here is one of the figures in this paper showing the distribution of the stars in our peak versus effective temperature, radius, and mass. And you can see how we focus on solar-like stars in our input catalog. The catalog has also been compared to the TIC and to other available stellar catalogs and shows very good agreement. So from the stars in this catalog, we will select our target fields, our final target fields that need to be fixed, as I said, 2 years before the mission. So what do we get at the end out of all of this? What are our stellar samples? Well, in principle, we have three main stellar samples to simplify a little bit. We have a core sample of about 15,000 dwarf and subgiant stars in the type range of F5 to K7, brighter than magnitude 11. And for these stars, we will get the full performance. That means we will have 34 ppm in 1 hour for stars brighter than 10th magnitude and 50 ppm for stars brighter than 11. And for these stars, we get the highest precision planet and stellar parameters. We get radii and astroseismology, and we will be able to do radial velocity follow-up on a large scale. Then we have the statistical sample. The statistical sample is addressing the fainter stars down to magnitude 13. We will observe more than 200,000 of them to get statistics of small extrasolar planets. So it will be very good for statistics. It will still give a very good radius precision, but we will not get astroseismology or radial velocity for most of them. Of course, we can still get some for some of them on the bright end, but not on a large scale, so to say. And in addition, there's a third sample of about 5,000 M-dwarf stars. This sample is, of course, covered very well also by TESS. So here there is a lot of synergy with TESS data. PLATO will extend the TESS data. PLATO is able to observe planets which are further out in the same systems detected by TESS. So I'm sure there's still a lot of synergy and interesting things coming also from M-dwarf samples when we are able to combine the data of the two missions. So what do we expect from PLATO? The goal is to have at least 4,000 newly detected planetary systems. And for about 100 of them, we can get very high planet parameter precision. And this will include small planets in the habitable zone, the number of which, of course, will depend on their frequency, which is not well defined yet. So another way to compare PLATO's versus TESS is to look at the noise levels. So that gives a feeling for the precision that one can obtain from the missions. So here in pink, we have the noise versus stellar magnitude curve for Kepler data. PLATO is here in light blue, Cheops in green, and TESS in dark blue. What we recall is the bulk of the Kepler planet detections had stars with magnitude less than 14. So it would be up here to the right in this diagram. The core sample of PLATO is addressing the bright stars, so brighter than 11th magnitude. And for these, we can get very high precisions, as you can see, even better than Cheops, obviously, because we have a larger aperture. And the P5 sample here makes the intermediate case. It's still brighter than Kepler data. So if you think about the science that you could do with Kepler data, but for brighter stars, yeah, that's what you can expect from PLATO. So how does this translate into the uncertainty of planetary radii? I already told you our requirement is to provide 5% radius precision for Sun-Earth analog for stars brighter than 11. So what we have done is model calculations based on the requirements that we have of the instrument to show, can it really be done? Can we fulfill these requirements? And this is the outcome. Here's the 5% line, and we can see indeed we can reach the requested precision. And for stars brighter than about magnitude 10, we can get a radius precision even down to 3%, and even better for brighter stars. So the radius precision coming from PLATO will be indeed very high, as we expect. So what is there to come to wrap this up? Well, what is ahead of us, in my view, is the decade of exoplanet and stellar characterization. PLATO will provide the main planet properties, that's their mass, the radius, mean densities, and ages, which with much higher precision than what we could obtain so far for planets on a large scale. Yeah, we know it can be done already from individual objects where these precisions have been reached, but PLATO will do that on a large scale, and that will include terrestrial planets in the habitable zone of some-like stars. There is a lot to be said about synergies with other missions. For TESS, of course, there will be TESS targets in the PLATO fields. We will be able to refine the planetary radii. We will be able to improve the ages of TESS host stars, either directly or by cross-calibrated age determinations with classical methods. But not last but not least to mention is the extension of the observing baseline. For TESS targets, we will have an observing baseline that almost spans a decade. And although we have interruptions in between, still for many cases of TTVs, etc., this will be very valuable. And then TESS as well as PLATO targets are bright, so they are well suited for transit spectroscopy with James Webb, with Ariel, with ground-based telescopes to come. And altogether, we will have a huge, a very rich data set for extrasolar planet characterization in the years to come for many science cases, not only for the frequency of small planets and not only for habitable zone planets, but also for planetary systems, architectures for planet evolution. The properties in a statistical sense correlated with stellar parameters, with the environment in the galaxy. And also, and that is something where the precision of parameters is most important, learn something about the internal structure of stars and the evolution, but also internal structure of planets. And with this, I like to thank the PLATO community that is working hard very much in this moment to make this mission real. But I also like to thank you for listening to this talk.